Swayam Prabha. Digital India. Educated India.
Response, that is the acceleration, depends on its mass. The same way, for the angular displacement, that is when an object or a rigid body is subjected to a moment or a couple, the response, that is in terms of the angular acceleration, will depend upon the mass moment of inertia of the body. So, when we will take up the topics on dynamics, you will see it in a more detail, but right now we will see how to determine this quantity, that is mass moment of inertia or the second moment of the mass. So, the concepts are nothing but an extension to the mass, because we have seen in the earlier lecture how to determine the second moment of the area and so forth. So, today we will see how to determine this second moment of mass. Or what we call as the moment of inertia of a mass. So, let us consider one small volume or an elemental volume delta m, which is situated at a distance of r from an axis, that is a prime. The response, that means let us say if a torque is applied whose vector is along this a prime, will induce a rotation of this mass about this axis a prime, and the response, that is in terms of the angular acceleration, will depend upon the distance as well as the mass of this particle, and that is why we are interested to compute this term, that is the moment of inertia of this mass about this axis, say a prime. So, the angular acceleration is proportional to r square times the mass of the particle or an object, and since we are assuming that the mass is very small mass, so there is no difference between various particles of this unit with respect to this axis a prime. That means, the distance of various particles of this delta m is assumed to be located at a distance of r from the axis. So, in that case, the angular acceleration is proportional to this term, that is r square delta m, when a torque is being applied. So, this term is the moment of inertia of the mass delta m with respect to the axis a prime. So, if we know the moment of inertia of a small mass, then we can compute the moment of inertia for a rigid body by considering elemental masses. So, here we are seeing one rigid body, and let us say we are interested in computing the second moment of this mass or moment of inertia of the mass with respect to this axis A prime. So, the moment of this entire mass with respect to this axis is nothing but summation of the second moments of the various particles or various elemental volumes that constitute this rigid body. So, let us say we have these masses delta m1, m2, m3, and there are infinite such kind of masses that constitute this entire rigid body. And let us say this mass delta m1 is situated at a distance of r1 from this axis A prime. Similarly, for other particles like delta m2 and m3, we know their distances, that is say r2 and r3, which are the distances from this axis A prime. So, when we know these quantities, then we can compute the second moment as the summation of the second moments of these particles. So, we write I, the second moment of this mass about this axis A prime, as summation of the second moments of the various constituent particles, that is r1 square delta m plus r2 square delta m plus r3 square delta m, etc. So, in the limit this becomes dm, and this is the integration over this complete volume. So, we have r square dm, and this is the mass moment of inertia of this body. And the unit, if you will see, is kg meter square, because the unit of the mass is kg and r square is meter square. So, the unit of the second moment of the mass is kg meter square. Let us say now we are interested to know the second moment of a given body with respect to the principal axes with respect to a particular coordinate system. Let us say we are interested to find the second moment with respect to x, with respect to y, z, etc. Because we have seen earlier that let us say a motion or the angular velocity can be decomposed along their coordinates, that is x, y and z. So, if we know their second moment of a given mass with respect to the various principal axes, then one can also analyze the motion by considering these quantities along with the components of forces and torque in those principal axes. So, in that context we are interested to find the second moment about, let us say, the various principal axes x, y and z. So, let a mass of value dm or a particle whose mass is dm be situated at a distance of r from the point O, which is our origin of the particular coordinate system. This vector r gives the position of this particle with respect to this axis. So, the coordinate of this point is x, y and z along the various principal axes. So, we have the second moment of this entire rigid body with respect to the axis y is I y y, which is equal to integration the distance of this particle from this axis, that is y axis, which is this distance, which let me call the projection of this vector on the x z plane. This quantity, that is ry, is the projection of this vector on this xz plane, which gives the distance of this particle from the y axis. So, we have integral ry square dm. This gives the second moment of this mass with respect to the y axis. But from the geometry, we see that ry is nothing but z square plus x square. So, this comes from this right angle triangle. So, we have from this right angle triangle, because this angle is 90 degree. So, I can redraw it for your convenience. So, this is your ry, this is z and this is x in the xz plane. So, we have ry square as z square plus x square dm, which is nothing but the coordinate of the particle along the z axis and along the x axis. Similarly, we can define the moments with respect to the other two axes, that is x and z, as Ixx, which is nothing but the second moment of this mass with respect to the x axis. It is defined similarly as integral y square plus z square dm, and Izz or the second moment of the mass with respect to the z axis as integral x square plus y square dm. So, in this way we can compute the second moment of this mass with respect to the principal axes. Let us now sum these values. If we sum all these values, we will see that this Ixx is nothing but integral y square plus z square dm. The same way we are adding up the other quantities, that is integral x square plus z square dm plus integral y square plus x square dm, which is nothing but 2 times x square plus y square plus z square, which is equal to this magnitude square of this vector r. So, that is what we write it as integral 2 times r bar's magnitude square. So, thus we see that this quantity, that is the summation of the second moment with respect to the principal axis, that is x, y and z, is invariant. That means, it is equal to irrespective of any coordinate system that we may take. So, let us take another coordinate system, say y prime, x prime, z prime, which is a rotated coordinate system. Even if you will compute the corresponding second moments and sum it up, it will be equal to this quantity as far as this origin point O is considered. Only if we displace this point, their second moment, the summation of the second moments will change. So, we see that it is invariant with respect to the inclination of the axis and only depends on the location of this origin O. Similarly, we can define the product of inertia. So, we have seen when we computed the product of inertia of an area, we take the distance of the elemental area from the corresponding two axes, that is, let us say if we are interested to find the second moment with respect to x and y, we take the distances from these two axes and compute the product. So, same way we have this Ixy, that is the product of inertia of the mass with respect to the axis x and y, which is same as Iyx equal to integral xy dm. And same way we have Iyz as integral zy dm and Ixz as integral zx dm. So, these three quantities define the product of inertia of the mass with respect to the two concerned axes. So, now we know the second moment of the mass with respect to the principal axis and as well as the product of inertia for a particular principal plane. If one of the coordinate plane, say xy, is the plane of symmetry, let us say if this plane, that is xy, is plane of symmetry, then it is possible to have two elements, say one in the front of this plane xy and the other at same distances, that is z, one is on the positive z and other is on the negative z direction. So, the sum of these two will become 0 and thus these two quantities, that is Ixz as well as Iyz, become 0. That is, when we compute this quantity Ixz, we have one element in the front of this plane xy and the other at the back, situated at equal distances z, and so their summation becomes 0. So, if a body has a plane of symmetry, then the product of the inertias, say in this case if the plane of symmetry is xy, then Ixz and Iyz will be 0, and this can be conveniently used to evaluate the product of inertias. Now, we extend the discussion that if the body is a body of revolution, say it is about the z axis, then it has now two planes of or all these three planes are symmetrical, that is, then we have Ixy is equal to Ixz equal to Iyz equal to 0, and also this Ixx equal to Iyy is constant, because we have this z axis as the axis of symmetry. The quantities that are computed, that is Ixz and Iyz, becomes 0, and also in the plane xy the body has a symmetry, and so this quantity, that is Ixy, also becomes 0. Now, we have seen the three principal moments of or the moments of the inertia with respect to the principal coordinate axes, that is x, y and z, and also the product of inertias with respect to the planes. So, these quantities can be conveniently written in a matrix form. We have this Ixx, Iyy and Izz, the second moment with respect to the axis x, y and z, and the product of inertia terms, that is Ixy Ixz and Iyz, and this matrix is symmetrical about the diagonal. So, we have this Iyx and Izx and Izy terms in the lower triangle, which is same as this upper triangle of this matrix. And we have put this negative sign. We will see the reason for that when we will use this matrix for the computation in dynamics. We call this as an inertia tensor because it follows all the laws of tensor transformation, and this is a very convenient way of representing the various moments in a concise form. Now, let us see how we obtain the parallel axis theorem for the moment of inertia of mass. The motivation is again that for a given body, if we have obtained the second moments with respect to a given axis, then we do not want to do the same procedure, that is by the integration, in order to find the second moment with respect to an axis system which is parallel. So, we would like to avoid that computation. So, here in this picture you see a rigid body for which, let us say, we have determined by integration the second moment with respect to this axis system, that is O y, O x, O z. Now, let us say we are interested to find the second moment with respect to an axis which is parallel to our original axis system. Let us consider now this y coordinate or this plane x z, and we have in the parallel axis this z prime x prime plane. Okay. G is the centroid of this rigid body, and the coordinate system, that is y prime, z prime, x prime, has its origin at this centroid G. So, this point G is located at a distance of x bar, y bar, z bar, or nothing but the coordinates of this centroid with respect to our original axis, that is O, x, y, z. Now, let us write these equations for computing the second moment with respect to the x axis. Let us say we are interested to find this quantity Ixx. As per our discussion earlier, this is equal to integral y square plus z square dm. Now, we write this y square and z square terms in terms of the centroidal coordinate and the distance of a element mass in the axis that is centered at the centroid. So, we are writing the coordinate of this location dm with respect to this transformed coordinate plus the distance by which it has been transformed. So, we have y as y bar, or it is nothing but say this is the distance y, this is equal to this y bar plus say a distance y prime, which is the distance of this particle dm in this frame, that is y prime g z prime x prime. So, we have this y square as y prime plus y bar square. In the same way, z square is z prime plus z bar square, z prime plus z bar square, let us now expand this and write. So, we have these two quantities, that is y prime square plus z prime square dm. So, integral y prime square plus z prime square dm plus the two quantities, that is 2 y bar integral y prime dm when we expand this, and 2 z bar integral z prime dm. Since these two quantities, that is y bar and z bar, are constant, we are taking it out of the integration, and then we have the last two terms, that is y bar square and z bar square, and since both these are constant, we take out of the integration and write plus y bar square plus z bar square integral dm. What are these two quantities? That is integral y bar dm. It is nothing but the first moment of the mass with respect to a centroidal coordinate. So, this term becomes 0 because it is possible to find the mass element which is having a negative y value corresponding to this mass, and so this integral becomes 0, as well as this integral, that is integral z prime dm, also becomes 0. So, we are left with these two terms, and that is what we write it as. What is this term? This is nothing but the second moment of the mass with respect to this axis, that is x prime, because we see that this is of the similar form of this, and we know that this is the second moment of the mass with respect to xx. So, this term is the second moment of the mass with respect to x prime axis, which is nothing but a centroidal axis. So, we write it as I bar. So, this notation helps us to know that this is a second moment of the mass with respect to a centroidal axis. So, this x prime axis is passing through the centroid. So, we have this quantity as I bar x prime plus, what is this quantity? This is integral dm is nothing but the mass of the body. So, we have plus m times y bar square plus z bar square. So, this gives the relation between the second moment of a mass when computed based on two parallel axes, that is xx and x bar. One has to again remember or keep it in note that this derivation is based on the fact that one of the axes is passing through the centroid. Now, in the same way we can write for the other two axes, that is y prime as well as z prime. So, we have I y equal to I bar y prime plus m, the mass of the body, times z bar square plus x bar square, and same way we have I z as I bar z prime plus m times x bar square plus y bar square. In fact, it is possible to write this relation for any axis that passes through a centroid and a parallel axis. So, that is what we see here. Let us say this is the rigid body and this is the centroid. So, this axis is the centroidal axis, that is b prime, and let us say in the space we have another axis a prime, which is parallel to this centroidal axis b prime, and it is situated at a distance of d. Then we can write I a prime, or the second moment of the mass with respect to this axis, is equal to I bar, that is the second moment of the mass with respect to this centroidal axis, plus m d square, mass into this distance square. Now, we have seen the parallel axis for the second moment of the mass with respect to an axis. Let us see now how to derive the expression for the product of the inertia. So, again we consider the same rigid body and the axis system, that is we have this x prime, y prime, z prime passing through the centroid, and we have another set of axis which is parallel to this centroidal axis, that is O, y, x, z. So, we write I x y as integral x y dm. So, if I write this term x as the summation of, if I write this term as integral, x becomes x bar plus x prime and this y becomes y bar plus y prime dm. So, now if I take the products and see, I have x bar y bar integral dm, which is integral dm is mass. So, we have m times x bar y bar. So, we have this term m times x bar y bar, and now if we take these two products, that is x bar y bar, then it is same as this terminology, and so it is I bar x prime y prime. The other two products, that is integral x bar y prime dm, is nothing but the summation of the first moment of the mass with respect to a centroidal axis, and same way this quantity, that is x bar y bar dm, integral of this term x bar y bar dm is again nothing but the first moment of the mass with respect to a centroidal axis. So, these two terms will become 0 and we are left with only two terms, that is I bar the product of inertia with respect to a centroidal axis. So, I bar x prime y prime plus mass times the distance x bar y bar. Same way we can derive and get the expression for I y z as I bar y prime z prime plus m y bar z bar. One has to again remember that these are x bar y bar z bar are nothing but the coordinates of the centroid, and same way we have the product of inertia I z x as integral z x dm, or when we expand it in this form and simplify, we have it as I bar z prime x prime plus m times z bar x bar. One has to note that these distances have to be measured from the coordinate system O, x, y, z. So, these quantities can be positive or negative depending upon the sign. So, this centroid is measured positive in this axis, that is O, x, y, z. Now, let us try to write this in the matrix form, that is the inertia tensor. So, we have this quantity Ixx minus Ixy minus Ixz. This vector or this tensor is the inertia tensor in the coordinate frame O, x, y, z. Now, each of these terms can be written with respect to the term in the centroidal axis by the parallel axis theorem. So, we apply that for each of these terms, and when we expand it and write, we have it as the inertia tensor in the centroidal axis, that is I bar x prime, I bar x prime y prime. This is nothing but product of inertia in this plane x prime y prime. Same way this I bar x prime is nothing but second moment of this rigid body with respect to the centroidal axis x prime. So, now we have, when we write all these individual quantities in terms of their centroidal axis, and the location of the centroid, that is x bar, y bar, z bar in this coordinate frame O, x, y, z. We have this as the inertia tensor in the centroidal frame of reference plus m times y bar square plus z square minus x bar, y bar minus x bar, z bar, etc. We already know that these are the coordinates that we have obtained from the parallel axis theorem. So, again writing it in this tensor notation helps in solving the problem, and also this gives a concise way of representing the various second moments of the mass. Now, let us see how to derive this mass moment of inertia with respect to thin plates, because they are predominantly used in construction, and many of the engineering objects involve these thin plates. And so, if we know how to compute the second moment of these thin plates, we can then go on to determine, let us say, the dynamic behavior of these plates when subjected to some torque or some forces. So, here in this picture you see a thin plate whose thickness is T, and it is constituted of a homogeneous material. That means the density of the material does not vary from one point to another point in the given object. And let us consider this axis A prime, about which we are interested to find the second moment of this plate. This axis obviously lies in the plane of the object. If we take this as an area element, then we have various elemental areas, say dA, which are situated at a distance of r from this axis A prime. The elemental mass is nothing but dA times T, the thickness, which gives the volume of that element, times the density of the element. So, rho T dA will be nothing but the corresponding mass element dm will be equal to rho the density times the thickness times this differential area dA. Since we are assuming that this T is constant and this rho is constant, so if we use this area element to determine the second moment, we have already seen how to determine the second moment of the area with respect to a given axis, then we can also find the second moment of the mass with respect to the same axis. So, that is what we are going to do now. So, we have this A prime, which is nothing but the second moment of this mass element with respect to this axis A prime. So, if let us say r is the distance at which this is located, we have integral r square dm, and dm we know it is rho times T times dA, and that is what we write here. Rho and T being constant, we take it out of the integration and we have this as rho T integral r square dA. And what is this quantity? Integral r square dA is nothing but the second moment of this area with respect to the axis A prime. So, we write it as rho times T times A prime. So, we now see the significance of finding the second moment of the area, because now we can find the second moment of the mass, which has direct relevance in terms of, let us say, the dynamics of the given rigid body. Now, let us take another perpendicular axis, say B prime. Again we can derive this and prove that this quantity I B prime is nothing but the second moment of this plate with respect to this axis B B prime is equal to rho T density times the thickness times I B B prime area, that means second moment of this area with respect to this axis B B prime. Now, let us take the perpendicular axis, that is C C prime, which is perpendicular to the given thin plate. So, we have already seen how to determine the polar moment of inertia, that means the second moment of this area with respect to an axis perpendicular to the given plane of the area. So, let us now extend the discussion to the second moment of the mass. So, let us say we are interested to find this second moment of the mass with respect to this axis C C prime. So, we have these various area elements in this thin plate situated at these distances r. So, again we can write the element dm as rho times T times the area element dA. Then we can find that this I C C prime, or the second moment of the mass of this plate with respect to this axis C C prime is equal to rho T J C, that means the polar moment of this area with respect to this axis C C prime, and we already have the relation between the polar moment of the area with respect to the rectangular second moments of the area. So, that is this JC area is equal to I AA prime plus I BB prime, the second moment of the area with respect to two perpendicular axes. So, now we have thus the polar moment of inertia of this thin plate, the polar mass moment of the inertia with respect to this axis C C prime as sum of the rectangular second moments, that is I A prime plus I B B prime. So, these discussions clearly follow our derivations for the area moments. So, for thin plates, if we have found the second moment of the area with respect to a given axis, it is possible to find the second moment of the mass without any additional lengthy computation. We do not need to again go in for the integration with respect to mass elements. And already we have seen that for many of the areas which are typically used in engineering construction, we have these values tabulated and thus can be directly taken for our computation. Now, let us discuss how we go about finding the product of inertia. So, here we are taking again the same plate, again it is having a homogeneous material. So, this density rho does not vary and thickness is also constant. Let us now try to find the product of inertia with respect to this axis A prime, B prime, C prime, which is the centroidal axis for this plate. Let us say C is the centroid and we are interested to find the product of inertia with respect to the centroidal reference frame, that is A prime, B prime, C prime. So, let us write these two quantities, let us say I A prime C prime and I C prime B prime. We will see that this quantity is 0. Why? Because if we take if we view this plate along this axis B B prime, say this is the axis B B prime, we have this C C prime axis and A prime A axis. Then we see that we have the mass elements which are situated at equal distances from this axis, and so in the integration they will cancel out. And since with this thickness T is uniform throughout, and see this frame, that is A prime, B prime, C prime, is a centroidal frame, we will see that this I A prime C prime as well as I C prime B prime, where we involve this axis C prime, about which the body has symmetry. So, these quantities become 0, and the product of inertia of this mass element in this plane, that is the plane A prime B prime, is equal to rho T times the product of inertia of the area, that is I A prime B prime area. So, now we see that for a thin plate we can determine all the quantities that are involved in the inertia tensor, those 9 elements of the tensor can be found by finding the area moments first and then finding the mass moments. So, for some examples, let us take first this rectangular plate. We have C, the centroid, and this centroidal frame A prime, B prime, C prime. Thickness of this rectangular plate is T, and the other two dimensions are A and B. So, we have the second moment of the mass with respect to this axis A prime as rho times T times the second moment of this area with respect to the same axis, that is A prime, that is I prime area. And already in our earlier discussion we have seen I prime for area as 1 by 12 A cube B. So, now the mass moment of inertia of this plate with respect to this axis A prime becomes 1 by 12 mass times A square. Now, same way for the other axis, that is B prime, it is rho times T times the second moment of the area with respect to the same axis, that is B prime, and this becomes 1 by 12 m B square. And for this axis perpendicular to the plane of this rectangular plate, that is C prime, we have this being the polar axis, we can sum the moments with respect to A and B. So, we have the summation of these two leading to 1 by 12 m times A square plus B square. Let us take another example. Here you see a circular plate. So, again we will see how we extend our findings for the second moment of the area in order to compute the second moment of mass for this thin circular disc. So, let us say we have a disc of radius r and thickness T, and we have this centroidal frame of reference A prime, C, B prime, C prime. We have the second moment with respect to the axis A prime, which is also equal to B prime. Why? Because we have seen that this is a symmetrical body and these two quantities are the same. We earlier computed the polar moment of inertia, and from that we computed these values for the area moments, that is I prime area. We found it to be 1 by 4th pi r to the power of 4, and to compute the mass moment we multiplied by rho times T. So, this becomes 1 by 4th mass times r square. mass is nothing but rho times the volume. Volume is this pi r square times T is the volume of this disc, and so from this we get this expression, that is 1 by 4 m r square. And the polar moment of this inertia with respect to the perpendicular axis, that is C c prime, is nothing but sum of these two quantities, which becomes half m r square. So, these examples just illustrated how we can extend our discussion for finding the mass moment of area and relating it to the area moment of the let us say the area of the thin plate. For objects, 3-dimensional objects, when we perform this integration in order to determine this moments, as we discussed for finding the moments of the area, it is convenient to choose appropriate elements in order to avoid, let us say, the double integral or triple integral. So, here you see one object which is having two axes of symmetry, or it is an object of revolution with respect to this axis O x. So, about this axis O x, it is symmetrical. So, it is possible to constitute a thin disc as the elemental volume for the integration. So, we can consider the mass of this thin plate and the second moment of this small disc element, and then integrate the same in order to obtain the second moment of the mass of this complete object with respect to any given axis. So, here we can write this I as rho the density times integral r square dV. We have taken out rho because we are assuming the body to be homogeneous, that means the density does not vary in the object. So, we can write it in this way. You can see for this thin element dm, or the mass of this element, is nothing but density times pi r square, the area of this element, times the thickness of this element, that is dx, or the small distance that we are traversing along the x. So, if we integrate this value, we can find the results. So, we have these quantities dix are nothing but the second moment of this mass with respect to the axis x, and the other two axes, that is y and z, also is defined in this way. Now, we can integrate these quantities to find the values. So, the moment of inertia with respect to a particular axis for a composite body may be obtained by adding the moments of inertia with respect to the same axis of the components. So, till now in the discussions we have seen that we are able to determine the second moment of the mass for, let us say, individual objects whose geometry is known, but for objects which are complex, we can still determine the second moment by decomposing into simpler elements for which the second moments are known, or it can be computed by integration. So, by the method of integration, we can determine the second moment of the mass for various simpler shapes, and it can be tabulated, and it can be used for determining the second moment of the mass for any complex object or objects that are predominantly used for our engineering structures, either machines or civil structures. So, let us see some common geometric shapes, like here we see a shaft element or a rod element. The second moment of this element with respect to the y axis and the z axis is the same, and it is equal to 1 by 12th of mass times length square. Because its radius is assumed to be small, the second moment of this shaft or the rod with respect to this x axis is almost negligible. Okay. So, now let us see for this plate. We have already solved this example in a more detailed way. If we have these as the dimensions, let us say C and B as the width and the length of the plate, and this all these frames of references that are shown are the centroidal frames of references. If we know the second moments with respect to these centroidal frames, then it is possible to compute with respect to any other parallel planes or axis. So, we have this Ix, the axis perpendicular to the plate, as 1/12 m b square plus c square, and the second moment of this plate with respect to the y axis is 1/12 m c square, and with respect to the z axis is 1/12 m b square. These things we derived in our earlier example. Now, let us take this rectangular or a cuboidal solid. Again we are considering this centroidal axis. We have the dimensions A as and B and C. Then we have this Ix or the second moment of mass with respect to the x axis as 1/12 mass times b square plus c square. So, you can try to quickly remember that these dimensions, that is b and c, are nothing but the dimensions in the plane y z. And the same way, when we compute this Iy or the second moment with respect to y, we have to take the dimensions in the plane zx. So, we have c and a. So, we have this 1/12 m c square plus a square, and same way Iz. For the disk, we have already found with respect to the perpendicular axis, it is 1/12 or sorry, it is 1/2 m r square, and Iy, which is same as Iz, it is equal to 1/4 m r square. For cylinders, we have with respect to the axis of the cylinder, that is Ix, it is 1/2 m a square, that is, let us say in this case a is the radius of the cylinder and L is the length of the cylinder, and we have the other two second moments, that is Iy and Iz, as 1/12 m 3a square plus L square. Here you see a cone. Again for the axis Ix, it is 3/10 m a square, and for the other two axes, that is y and z, it is 3/5 m times 1/4 a square plus h square. The other common interesting element is the sphere, whose, let us say, radius is a. Then we have all the second moments, that is the second moments with respect to the principal axis is y, z, x, all being equal to 2/5 m a square. All these values can be proved by the method of integration, and these values, once available in the tabular form, can be now conveniently used for determining the second moment of the mass with respect to various axes for any parallel axes. So, in this lecture we saw how to determine the second moment of the mass, and we will continue in the next lecture. We will see some problems in this topic.